I think we can start. So, I'm the only one that's standing before you and going home, drinking a beer, reaching the airplane, so I hope it will be, thanks for staying. I thought I wouldn't have more than 10 people, but I try to do it interesting. So my name is Assaf Araki. I'm from Big Data Analytics team. We are located at Intel and we are located at Israel. It's great having a conference in Europe, not needing to fly 18 hours to the West Coast in the US. And Berlin is amazing. So just a little bit about our team and what we are doing in order for you to have a context of what are we needing. So our mission is to have analytics as a competitive advantage to Intel. And we do it in two main routes. One is operational excellence, which means we want the operations of Intel run at best performance, reduce the cost of the operation, or reduce risk, or increase revenue. So we work, Intel is a chip company. We design chips, we manufacture them, and we sell them. That's simple. And we work with those three business units, with the design of the chip, to cut the validation and verification of chips, find bugs earlier, classify bugs, tell the designer themselves whether this bug that been found is an old bug or related to a bug that already been fixed or known, or is it a new bug from a new cluster and you need to give a high priority for that. In the manufacturing is reducing the test cost. And in the sales and marketing, is increasing sale by giving an online seller engine recommendation, which company to contact, recommendation system, what product to offer in order to increase the revenue of Intel. So we have, in our team, we are a little bit over 100 people, and third are data scientists. And when I'm saying data scientists today, everybody is a data scientist, but for us, data scientist is a PhD or master in machine learning. That's the entry level. A little bit more than a third are big data developers, distributed computing developers, and the other are a project manager or system analysts with business acumen. So we use machine learning and sometimes big data solutions in order to solve this problem. This is for 50% of our work. In 2014, we had a return of investment of almost $200 million. For reducing the cost of operation or increasing the revenue for Intel. The second mission is help Intel win the era of intelligent machine, and that's how we are leveraging, we are actually the engineering arm under the data center group. And we started 3 years ago building a stream analytics solution. We need an analytics solution for the stream analytics for the IoT domain. The ones that in the market didn't fit us back 3 years ago, so we built our own stream analytics cloud, which I'll review today. One of the projects we are doing is around Parkinson research project, and I'll elaborate a little bit more about this project and the requirements. And of course, as well as we have extensive knowledge in machine learning, we are part of the machine learning strategy of Intel, how machine learning workload benchmark can be accelerated on hardware. So this is an overview for the team, and let's dive into, so you've seen we are focused mainly in machine learning. That's what we want to do. We want to build a model offline and doing prediction on the stream. So a little bit about the IoT challenge. This is an overview. We have these things. These things can be wearable. This thing can be sensor in the manufacturing or in the streets. They're connected to the internet. They're sending data through some kind of ingestion layer into the cloud. And in the cloud, we have the infrastructure. On top of it, data platform that manage the data. Then we run our analytics and we supply our services. In this talk, we'll focus on the ingestion layer itself. So I choose a use case which is not a standard use case for IoT, but I choose it because it's interesting and it's unique and it's done for a good cause. The guy in the left is, I don't think anybody recognize him. This is Andy Grove, one of Intel founders. He has Parkinson for the last 15 years. He has his own fund for Parkinson research, and he read an article in the New York Times on big data, and he came to one of the engineers at Intel that's apparently managing all the data center division, and asked for what Intel can do with big data in order to help Parkinson. He collaborated with Michael J. Fox, his biggest foundation for Parkinson research. Over 60% of the research being done by this fund, and they turned to us, and we leverage basically a smartwatch, a commodity, smartwatch, $99, and a smartphone application in order to help the Parkinson research. So what we are doing, we are giving the patients a wearable. This is a Pebble watch that they can wear, and they have an application on the smartphone which transmit the data from the wearable itself into the smartphone. The smartphone as well has its own sensor, so we leverage as well the smartphone sensor. We send the data into the cloud, we run our analytics, and then we have additional 3 customers. So the customers are first researcher. We want to collect 24/7 data on thousands of patients in order to help researchers to hopefully have a breakthrough in the research of the disease. But meanwhile, we can help clinicians have an accurate report on what's happened with the patient during his day-to-day life, because today the clinician see the patient 3-4 times a year. We ask him, how are you doing? And he doing some test like which is don't have a real hard measurement that you can compare over time. And at the end as well, we can leverage this platform for the pharmaceutical company to run clinical trials. So what we are doing, we are bringing a small set of patients into the clinics. We run our test, we create and validate our algorithms and measure them. This is what's been done today by pharmaceutical company. It's very expensive, it's millions of dollars. You bring 20, 30 patients for 5 days, and you give them the wearables themselves, and then a lot of people track them and document what they've been done. But we want to scale, and once we validate our algorithm, we go and generate insight on thousands of patients. So what we are doing, we are create objective measurements, no objective measurement for the Parkinson's disease. We want to track the patient 24/7 during his day-to-day life. First, in order to have the data, we need to give him something that is usable for him, that's beneficial, that he can manage his day-to-day life, and then we get the data. So we identify tremor, and we measure it. We create activity level, which is objective measure. Today, Parkinson patient, as they're more active, the disease progress slowly. So it's really important for them to be active, and they need to know how much they are active now versus the days before. We detect sleep. The patients of Parkinson don't sleep very well. They wake up a lot of time, including taking medicines, and they need as well help to manage their sleep. And as well, we identify gait, whether the patient is standing, walking, climbing stairs, and so forth. And these are already in production, and we are adding much more capabilities. The second one is helping the patient in medication reminder, medication reporting. We do control tests, like we ask the patient once in a month, walking 10 steps, and we can measure it over time and see the degradation. And of course, we add other measurement capabilities. We can do configurable data collection, which decide whether we want to collect the raw data, which is collecting 50 hertz for clinical trials, or we want to collect only aggregate data. And as well, you can have Pebble notification and so forth. So you may ask yourself, okay, this is really interesting project, but is it really big data? So this is a clinical trial. So we have 30 patients for 5 days. Each patient, we measure accelerometer in 50 hertz, and it creates 1 gigabyte of data per patient per day. So it's 150 gigabyte of data weekly. That's nice. If we want to track them 500 patients for a month, it's 15 tera a monthly. But we want to reach by the end of the year 1,000 patients. We already reached 300 patients, and the goal is to reach 1,000 in US and Europe by the end of the year. So 1,000 patients for a year is third of a peta. This is definitely a big data problem, and 1,000 patients is small. We have 6 million Parkinson patients around the world, only 1 million in the US. So let's look on the solution and then dive into the streaming layer. So this is our solution. Let's start from the top. We are using PebbleWatch and an Android application. We're right now building our iOS application, and we'll release it by the end of the year. All the other platform beneath that, we are trying to use open source and not commercial, and be agnostic to any platform that we are using. This platform is not only used by the Parkinson project, it's used as well internal, within Intel for other projects, but that's the reason we build it open source, so we can transfer it between public cloud and private cloud. So we use, for Parkinson, we use Amazon Web Services. Our analytics layer is Spark that runs the batch. Our storage layer uses HBase. Based on Cloudera, we use HBase for the data and MySQL for the metadata. Our ingestion layer is based on the broker is Mosquito, and we use Akka and Kafka, and the stream analytics is on top of Akka itself. So today in the talk, I'll focus in the ingestion and the stream analytics layer that we started a little bit less than 3 years ago. So before we start looking on the platform, let's talk at what are the requirements for a platform like that. So the two ones are basically a basic requirement from any distributed computing platform. We want it to be linear scalable, that once we add more and more patients, we can add more and more nodes and scale. We want high concurrency and high throughput from the platform. And as well, we want fault tolerant. We don't want to lose data. So we assume that we will have a failure in the system. So we don't want to have any one single point of failure from one hand, and the other hand, when we have a failure, we want to have the ability to recover from a failure. So these are basic, but it's less interesting. The more interesting is the requirements that we have here beneath. We want the pipeline to be smart, which means we don't want only the pipeline to transform data in order to put it into the repository. We want to apply analytics on the stream, starting from very basic like rules and going into machine learning. And once we reach some kind of event, we want to actually trigger when we need. We want it to be personalized. It could be personalized per on the level we decide. It can be personalized per sensor. It can be personalized per device, and it can be personalized per user. And for example, if you are in the manufacturing domain, so you might want to do a change detection for your machine. Is there a change in how machine behavior? And you might want to do a change detection that is multi-sensor or multi-device. So you need to be agnostic and be able to have personalized and be agnostic on the level of personalization. And you want to maintain a state. And the state is required for machine learning. It can be state of from very simple state like mean and standard deviation, and more complex than that. And at the end, last but not least, it needs to be easy to use for the developers. Developers should be focused on develop their logic and all the peripheral that return every project that for management and scalability and fault tolerance and need to supply by the solution itself. So let's look on the architecture. So this is the smart data ingestion, and we'll start with the Left side with the broker, MQTT broker that's been built for the IoT domain. His main problem is not scalable. And we solved that by putting a load balancer and creating several broker in order to have ability to scale. And we as well use Kafka. Kafka, as you heard a lot in other talks, I won't repeat it, but it's a durable, persistent, and distributed storage. So the MQTT broker and Kafka give us a scalable and persistent broker, which means the data is fly from the internet and it's stored in our cloud, but we didn't do any transformation right now. The second part is Akka. Akka is an open source, but by type safe, is an actor model based, and it's as well distributed and scalable. And this layer give us the ability to process data, run our rules, and run our analytics, and store the data into the data hub itself. So that's why we have a processing and stream analytics, and we have a whole solution that can answer our needs. Let's dive a little bit into Akka and see what Akka is. So Akka is based on the actor model. Each actor is having a small piece of code, a granular piece of code that can run some kind of logic. Each actor can connect with other actor by sending messages one another. It's high performance, fault tolerance, and scalable. So that way we can divide our logic into small pieces, which is we have the best performance, and we can now what we do with these small granular pieces of code. We combine them. So combining several actors create a topology. A topology, this is basically our logic of what we want to do. We can put millions of actors on one single Akka nodes, and of course it depends on how much data they are holding and what they are doing. So for here, there is an example of a Parkinson's disease topology. We have a subscriber that subscribes to the Kafka. You get the data, he parses the data, then he unzips the data because we compress the data in the Kafka, and then you can use, there can be several actors. One can run real-time rules, predefined rules. One can do aggregation if we don't want to save the raw data, and one can manage the analytics. We can run sleep quality, but you can run as well chain detector or tremor, and so forth. And at the end, it's writing it into the HBase itself. So we didn't invent a Akka. This is what we got out of Akka. So what we added is the manageability on top of that. We created a management layer. We call it Pigeon. It's where all the work that first we want developer to be focused on developing the logic. So all the services of subscribe to a data stream, taking your code and pushing it and creating an actor and deploying the topology should be in Pigeon is configurable driven. Addition to that, we leverage the built-in capabilities within Akka to manage fault tolerance. It's not implemented in Akka, but Akka supply the building block for you to build the manageability of fault tolerance and recovery, and we implemented it inside Pigeon. So in order to additionally be able to deploy this solution and be used not only for Parkinson, but inside Intel or on other clouds, and be able to deploy very fast cluster, even for testing or production, we're leveraging CoreOS and Docker. Docker, we had, I think, yesterday a talk here about Docker. Docker basically is an open source project that automate deployments of applications inside a container themselves. So you have a container of maybe Broker or Kafka, or but still this is a notion of one node, and you want a notion of a cluster. So CoreOS is a lightweight open source operation system based on Linux that has a notion of clusters, and he can manage the cluster itself. He manages the container and create a cluster aware. If one Docker node is failing, he can recover. So that's why we have the ability first to break our topology into the building blocks. Some solution doesn't need MQTT. Some solution doesn't need persistence, so you don't need a Kafka. You can create whatever you need, and you can create a notion of stream analytics from using CoreOS and Docker. So to summarize, we have an IoT data ingestion layer that is beyond moving data and transforming data. We applied change detection and anomaly detection algorithm. Some of the change detection, for example, it's under patent right now. It created a multi-sensor change detection algorithm on top of Akka. We had anomaly detection, periodicity, and string classification. We have deployed it in a way that it fault tolerance and enables stream analytics, and I think this is the edge of analytics and machine learning for streams. And of course, it's used for other IoT projects. We have other projects in the IoT domain, some of them within Intel, on the manufacturing domain, some of them outside, collaborating with other company. That's it. It was quick.
I see that you're using Spark for a basic analytics processing. Are you planning to use Flink or trying it out?
So I heard about Flink a long time ago, but attended last VLDB and I tried, and I was impressed from the gap that Flink closed in the last year, and I can say definitely we will try it for the stream. We have our own special requirements, so we are taking Akka is more flexible for us, so we're taking models of machine learning and implemented them inside of an actor. So we need to validate and see if we can do it in Flink. But definitely, yes, we will test it. We didn't test Spark Stream, for example, even tried it, because we know it's not ready.
One question concerning the ingestion part. I saw you show Mosquito plus Kafka. Why just don't use one of these systems? Why both?
Because Kafka gives us the persistent itself, but it's not a broker. So we need a broker. We need to take into consideration. So maybe the last version of Kafka can supply it, but before that it wasn't supplied. Okay.
What was the throughput that you can achieve with that entire stack? So the streaming throughput from the events being generated into Kafka or into the processing layer?
So I really don't have any data on throughput. If you want, I can send it to you. I'm not recalling a throughput there. Sorry.
What kind of latency did you need between when the device was measuring something and when it went into the modeling/presentation layer?
So you're referring for how real time we need for the prediction? Okay. So it's not a notion of millisecond in our use cases. It's more in a notion of seconds, several seconds. So it's usually most of the project, especially in the enterprise domain or the IoT, a lot of them send data sensor every several seconds. So the notion of urgency is not big.
Are you planning to open source Pigeon or no?
So Intel has additional projects. As everything at Intel, there are 3 teams that are doing the same thing and looking who will reach the final line first. And we are collaborating with additional team that doing a similar project that what we did with Pigeon, and we are now collaborating to have one solution, and we want to put it in the open source. That's the goal.
So what's really the use case for using streaming at all in this case? I mean, would it be sufficient with just batch processing in this case?
It can be for a lot of them. It can be sufficient for with batch processing. But I think that a solution like that can give you benefits for a task you want to do, that it's more flexible and easy to do them. You don't need the entire data. We have all the data in the repository. We don't delete any line of code. At the end, searching the data, running your batch and searching the data in the HBase itself and the connector between the analytics and the NoSQLs are really bad. The performance there are really bad. So I think, it's just, at the end, it's an 80-20. Most of the problem you can solve on a one machine. Why do sampling and that's it. Why you need distributed computing? Because I think it's afterwards open you to other capabilities that you didn't think about it. We did, big data before we have clusters.
Have you compared the performance between your Pigeon framework and other kind of frameworks available in the open source? So
we started. So Pigeon it's only the management. It's not the processing.
Eureka.
Yeah. So we started 3 years ago, and there wasn't something. We never evaluated against Spark Stream or Flink or anything that exists.
Maybe a last question?
Are you doing any kind of time series analysis on the data that you have, and how are you storing the time series data in HBase itself?
Yeah, definitely. So, but you're referring to the learning phase, right?
Yeah.
So the learning phase is done in batch. We are not learning on, there is no online learning on our solution. We learned on batch. I think the reason it's more easy, you have more algorithms. You usually don't have the notion of needing, the urgency to build a model every several minutes.
Okay, I mean, do you see yourself going towards a Lambda architecture kind of a thing, or a Kappa architecture in the future, as you have more data coming in, and when online learning becomes a requirement?
I think the answer of if online learning become a use is a notion of breadth of algorithms, a capability. I think this domain is really, really young, and everybody is going right now for deep learning. So that's where the focus, everybody doing deep learning for everything. And it's batch as well. It's just needing more computing, which is great. So I don't see online, all the professors that I'm seeing in the university that were against deep learning still 2 years ago, they're all doing right now deep learning. They're focusing there.
Thank you.